like to remind you there is a FabTech mobile app for download that will help in navigating around FabTech and providing other valuable information about the show. Also, as a thank you for attending a conference session, most all the presentations being offered at the FabTech conference will be available for viewing online approximately 2 weeks after the show for all registered FabTech conference attendees. Look for an email with instructions on how to access these presentations after the show. Finally, there is a short electronic survey with QR code and instructions placed about the classroom. Please take a minute to provide feedback on our session today. My name is Patrick Coonan, and I am the first presenter in today's session. So, my name is Patrick Coonan. I am a project engineer at Sharp Products. Today we'll be talking about tube bending best practices, processes, and outcomes. A little bit about myself. Not a fan talking about myself here, but back I went to school at UWM, studied mechanical engineering, and there is when I got involved in manufacturing engineering. Started at a large mining company, moved into fast-paced manufacturing, getting involved with programming multiple different types of manufacturing equipment, ultimately landing me into the tube fab business. I've been involved with tube bending for approximately 10 years now. Current role and responsibilities right now, I am managing engineering and estimating. Currently review incoming RFQs to help determine scope based off of customer requirements. From there, we have to look at internal feasibility, whether we can actually produce the parts that the customers are looking for. And then from there, we work on DFMs, which are designed for manufacturability. We will work with the customer to hopefully cut costs, or if we're unable to manufacture per to the design, we will work with customers to be able to manufacture ultimately on our equipment. What we'll cover today is applications. What is tubing used in? What is needed to start a job? Processes for tube bending and forming. Materials and tooling. Challenges that are involved in tube bending. There's no way around them. And then we'll finish with a Q&A session. I'll leave this interactive. Feel free to raise your hand and ask questions while we're going through this. Before we get started, how many of you, with the raise your hand, work for an OEM currently? Okay. How many currently work in fabrication? And how many work in manufacturing but in another sector? There's a lot of industries and applications where tubing is used. You have your aerospace. A lot of times aircraft exhausts you use tubing in aircraft exhausts. Mostly, your stainless steels. Sometimes you will have your exotics, Inconels. Agricultural, a lot of times get involved with the structure, the chassis of combine units with their larger structural bent tubing. Also, seen in the chairs that you guys are sitting in, tube bending was used to form the actual structure of that chair. Medical, it's used in hospital beds, incubators, are just a few. And then recreation. Tubing is used highly in a lot of chassis and recreational, snowmobiles, four-wheelers, etc. The project. What is required to get a project started and why? One of the main ones is the application. You need to know what the tubing is being used for. It will help to understand tolerance stack-ups. If you have multiple parts with a tolerance that you're trying to hold, ultimately going into a weldment, you need to make sure that those tolerances are taken into account. So in those applications, they can be chassis, exhausts, they can be fluid lines, so you might only be worried about A to B with a bunch of clearance that you have to, because a lot of times with tube bending, and when you're designing tubing, a lot of times that is the last design, so that you're left to work your way around whatever's been put in place from the manufacturer to begin with. So there's all kinds of applications that tubing is needed in, and we need to know that to be able to quote it and verify if the job can be done. On top of that is the EAU, which is estimated annual usage. This will determine how you're going to manufacture the bent fabricated tube. EAU is it's a needed number because if it's a low prototype quantity, you're going to manufacture that tube differently than if it was a high production 10,000 plus parts. equipment, and faster processes, because you're not looking for just a prototype to test. Along with the application EAU, you're going to need a drawing and a 3D model of some sort. Now with the drawing, most manufacturers, when looking at fab tubing, can take that blueprint and get off the information they need. And that information in tube fabrication that you're looking for is usually your XYZ and LRA data. The XYZs are your theoretical intersection points, the bends. And the LRA data would be, the L would be the length between bends, the R would be the rotation on plane of the bends, and then the A would be the angle of bends. With a 3D model, we can, the manufacturer can actually pull that information off and utilize it to verify if they can manufacture the part to print. So if, when designing this, sending the print with a model would be the most time efficient way to get a quote back to you on whether a part could be made per print. Another huge requirement in the project is knowing the outside diameter of the tubing. That's critical because your tooling is based around your OD of your tube, whether it's structural, rectangular, or square, or round. The tooling needs to be designed around that outside diameter. It needs to take into account. Now, tubing is cross-sectional. You have a hollow inside, so there is other tooling required, but your main clamp and bend die are based off of your outside diameter. On top of the outside diameter, the customer also needs to provide or create a center line radius, not the inside or outside radius, but the center line radius of the bent tube. That is the neutral axis of the form. So, for example, if you had a 1-inch OD tube with a, you say a 1-inch inside radius, your center line radius would be 1.5 inches, and that's what you would manufacture the bend die to bend that product out. Other keys that you need for the project are characteristics of the material. The thickness of the wall is crucial, along with the OD of the tube. Types of the material to be used also are crucial. You have your aluminums, stainless steels, and steels. Those are your three main materials that you see a lot of people bending tubing on. But you will get your exotics like Inconels and titaniums, but those are more rare. You see a lot of your 304, 316 stainlesses. Your mild steels, you'll have A513, T1 electric welded up to T5, which is DOM. And then your aluminums ranging from your 6000 series to 5000 series. Of course, each metal is unique. There's different characteristics of all the materials. So each metal you have to know what each metal you're going to use because it's going to dictate the manufacturing process. Bending methods, and I will have videos following for each one of these after we go through all this. Bending methods. The first and what is used in most job shops is your rotary draw bending, and that's where you're going to have a physical bend die on a tool post, and the tubing is going to bend around that bend die. Then you have your freeform bending. That is, it's the simplest way to put it is like extruding a tube. So a mill extrudes material. Same way with freeform bending is the tube is actually pushed through a ceramic collet die, and the die is on a free moving axis, and you program it, and it can create bends on bends. So it's good for helical bending, going from a roll to multiple 90, 80, 70 degree bends. It's capable of transitioning bend on bend. With rotary draw, you need straights between each bend to actually bend out the product. Freeform, you do not. Then there is roll forming. Roll forming takes over once rotary draw bending bend dies get too large. So think of it, center line radius, it's the radius of what you're bending. So it's actually a diameter. So as that radius increases, your machine no longer can hold a bend die big enough for the radius that's required by the customer. From there, you then have to go to roll tooling, and that's considered roll forming. So now you've replaced the bend die with rollers. Sometimes you can even leave the bend die and just replace your clamp with rollers. You take so what happens now between rotary and roll, rotary draw bending will actually take the tube, which you'll see in the videos, and it'll clamp it and bend it. Roll, you'll actually see the back axis will actually push the material through rollers, and the rollers will create large sweeping radiuses. So you'll be able to create a larger bend radius with roller tooling versus rotary draw. Finally, there's compression bending. This is used on high production, high EAU jobs. Rotary draw bending can be controlled with a mandrel. Compression does not use a mandrel, so you're looking at all empty bending. So with compression bending, your bend region cannot be critical. If you have a highly cosmetic bend region where you can't have any deformation, compression bending is not going to work for that application. Compression bending is, your simplest example would be a generator frame that you see in Home Depot. A lot of those are going to be empty bent where you're going to see deformation in the bends. But it's used for high EAU. It helps get parts out faster. You can do multiple bends in one shot. With rotary draw, it's one bend at a time. Tooling. This tooling page that we're going to discuss is all based off of rotary draw. I will throw in different topics in regards to the other roll forming off of here, and then with the videos you guys will be able to ask questions as well. So with rotary draw bending, this is the tooling that you need for every job to be able to execute a formed tube. Bend die is your most crucial. That is going to be this right here. And it's located on your tool post on your CNC tube bender. Now I say CNC tube bender, those are the new ones that you can program for the computer to automatically bend the tube. They also have manual setup benders where you can bend one at a time, and then, So then with the bend die, which can be whatever centerline radius you need on the tube. With the clamp die is directly across from the bend die. What the clamp die does is it comes in, and on this bend die, which isn't noted here, on the front end, there's an insert in the bend die. Now the insert can be machined into the bend die, or it can be added afterwards by screwing it into the machined out section, which at that point then you can change out your inserts for grip power. When I say grip power, that's where the clamp die comes in and actually grips the tube for forming. With the bend die and clamp die, you will hear in the industry, tool builders will talk about smooth clamping, serrated clamping, and knurled clamping. Smooth clamping, you're going to need a longer clamp and a longer insert because you're gripping with with a smooth bore clamp on a tube. Or if you need, so for example, in order to draw with the straights between bends, if a customer would come and say, we need a 6-inch straight between bends, but to manufacture it, the insert would need to be 12 inches for it to not slip in the bending process, you would have to go to somewhat of a serrated or knurled clamp so that you get more grip into the tube to prevent it from slipping. And then you would be able to shorten that clamp length. Along with the bend die, clamp die, you also need the pressure die. The pressure die is what rides right behind the clamp die. So as the clamp die closes on the bend die, the tube gets constrained between the bend die and the clamp. The pressure die also follows in and clamps to the back side of the tube. Now the pressure die isn't putting as much torque on the tube as the clamp die. The pressure die's job is to just actually follow. So that's why it says pressure die here. There's also the term used follower die is also used in tube bending. So pressure die / follower die can be used interchangeably. That is to follow and keep the tube from kicking out on the backside, because as you compress and want to form the front end of the tube, naturally the backside of the tube is going to want to kick out, so that pressure die is meant to keep that tube in line, running in a linear pattern. And then it also gives you ability to control your elongation in the bends too. With a certain set parameter, you can have that pressure die follow at a certain speed too and stretch the material more if need be. Now, along with those three, you sometimes need a wiper die. Not always do you need a wiper die. A wiper die is going to be used mostly when your wall factor and D of bend increases. We'll get to that. When I say D of bend, there's terms 1D, 2D, 3D are your general your bend difficulties, I should say. 1 is your most difficult. That is the OD of the tube is the same as your centerline radius, which is a very, very tight bend. And a lot of times you have issues with wrinkling and such. What the wiper die will do on a tight 1D high wall factor bend is right back here, there's a gap that is left in the bending process. And what the wiper die will do is you actually mount that to the back side of the bend die and feather it close to tangent, and it tells the material to form in a linear pattern instead of wanting to find the path of least resistance and flow back into that cavity, which creates wrinkles on your bends. The wiper die will tell that material to keep flowing linear towards the bend die, eliminating those wrinkles because you no longer have that gap for the material to flow into. With the wiper die, you also need a mandrel. Now your mandrels can be plug mandrels. And that means just the mandrel is right here inside the tube. You can have plug mandrels, which is the mandrel body on a mandrel shaft, and it's just that. You feather the mandrel body to the nose to tangent, and then you can bend. A lot of times you're going to have a little bit of deformation in the bends with a plug mandrel. But on top of that, as your bends become more difficult and you want a smoother bend, you can add balls to that with links. So what you do is you have your standard plug mandrel, but on the end, there's little linkets with ball mandrels on the end. And depending on the bend difficulty and the smoothness of the bend that you're looking for, you can add as many balls as you need. From plug, which is 0 balls, up to, we bend in-house 6 ball mandrels. And what happens is those balls flow through the bend and help keep the ovality of the tube not deform. With all of that, you also need your collet. Collet is just like a drill chuck. You have to load a bit into a drill, same with the tube. You have to put the tube somewhere. So the tube is accepted by the collet at the x-axis of the machine, and that's what drives it forwards in the bending process. All those are critical for a very accurate bend, but a wiper die and a mandrel are not always needed in rotary draw forming. Depends on what the application and what the customer is looking for. Some of the challenges in bending, what I talked about earlier is tight radius bending, specifically 1D bending. 1D is the center line radius divided by your diameter of your tube. So that's how you can always figure out your T of bend. The higher that number becomes, the easier your bend becomes. So for example, if you have a 6-inch centerline radius on a 1-inch OD tube, it would be considered a 6D, which is a very easy bend compared to a 1D bend. Now a 1D bend is a 1-inch diameter tube on a 1-inch centerline radius. Much more difficult to execute. At that point, that's where your material properties come into play quite a bit. Your elongation, yield, and tensile play a huge role in that because your material likes to crack when you're bending tighter bends, especially your 60-61 T6s and your hot roll pickle and oil steels along with DOMs. Those you're all going to want to have 3D or higher to prevent cracking. Otherwise, you're going to have to look at annealing the material, and annealing the material would be softening it compared to its raw substrate specs. You're actually softening the bend zones to be able to form that material and not crack. What also plays a role in that is where you place your weld seam when bending. Weld seam on some tubes, there isn't a weld seam on all tubes. Specifically DOM is drawn over mandrel, there is no weld seam. That tubing is very difficult to bend without annealing. You would need a larger D of bend to be able to execute that without cracking that material. Thin wall material also plays a huge role in creating a challenging bend. The higher so this is where it's different from the D of bend. As the D of bend increases, the bending difficulty is lower. But with the wall factor, it's opposite. As that wall factor increases, the difficulty of bend increases. As your wall factor gets lower, the bend becomes easier. So for example, a 4-inch OD 304 stainless on a 4-inch centerline radius with an 035 wall is a very high wall factor and a very low a very low difficulty of bend on the 1 to 3 reference scale. That tube would be very, very difficult to bend, and I do not recommend ever attempting a high wall factor, low D of bend to anyone just getting into bending. It's very, very difficult. That's where your tooling setup becomes very crucial. From your mandrels to how many balls you run to your wipers, everything has to be set up perfectly to be able to execute something like that. Another huge challenge is parts with existing holes features. Same with sheet metal. When you're press braking sheet metal parts, features around the bend become a nuisance. They're a pain. They can crack, they can oblong, they can crush, all things that the customer, the end user, does not want to have. And then ultimately your part comes out of spec. So that is one huge issue in tube bending. If there's a hole on the bend on the outside, doesn't matter the size of that hole, it is going to crack. On the inside, it is going to crush, and there's not going to be a hole left. On the outside, it's going to split open. Now, there is ways around that. You can find a manufacturer that would have a punching machine, drilling machine, or a free axis laser that can actually put the holes in afterwards. Holes in bends on bending tube are a big no-no. That it just does not work. But you can put holes near bends, and you can orientate them on the bender. However, general rule states that you should be at least 3 times the diameter away from the tangent point of the bend. And the tangent point would be right here, the transition from the bend to the straight. So from that point, they say as a general rule, 3 times the diameter to the edge of that hole. Not the center of the hole, but the edge of the hole, to help prevent it from deformation in the bending process. Now there are ways around that. The manufacturer of the tubes can control the deformation of a hole. So if the tube would be, say, tube lasered prior to bending, you can actually laser the hole oblong or odd shaped, taking into account what kind of deformation is going to happen in the bend, so that the hole actually becomes perfectly round after you're done forming it. Now, that only works on a specific heat of material. Every time the heat of material changes, that offset change that you've done on the hole most likely isn't going to work for the next heat. That's another huge issue. Heat changes on batches of material like sheet metal. It's even worse with tube bending. From heat to heat, you have to literally redo your developed length if you're working in a tight tolerance envelope. So say the customer wants to hold 30 to 65 thousandths over a couple bends, you're going to most likely need to redevelop that tube upon a heat change. So that's why it's really crucial when working through this that heat changes are made clear to whoever's manufacturing it, and if possible, large mill runs of the same heat will work in everyone's benefit. Production orders for small runs, those also play a huge challenge, because what works for a small run fabrication job is most likely not going to work for a large production run. And the reason behind that is that small runs, prototypes, customers are usually willing to pay more for the cost of that part, where at production runs, piece costs is crucial, and at that point, that's where 10 cents is make or break. So that's where, when developing tubes for a production run, might be different than a prototype run, and that has to be taken into consideration. And when talking with whoever is going to manufacture the tube, if you can go into that with those details, letting them know, hey, this is prototype run, this is where we want to get to with production. Most of the times the manufacturer is going to be able to work with you with the equipment they have to get that prototype out for you. But when it comes to production, that's where there might be more of a conversation to buy equipment or whatever it may be needed. It could even just be tooling to get out that part per print, and then to actually do it in a very efficient manner to keep costs down as well. Another challenge is making sure you have the correct tooling. So the bend die and clamp die and pressure die all stay pretty much the same, because those are all based off of the OD of your tube. However, again, with different runs of material, your wall thickness fluctuates per ASTM standards. Every mill that produces material has a range that they can work in on their material thickness. That causes problems with tube bending because the mandrel runs on the inside of the tube, and that is usually sized within a couple thousandths of what the ID of that tube is. So as you get different heats in with different wall thicknesses, now your mandrel that did fit on the last run no longer fits on the next run. Now it may be too big or it may be too small, depending on the application and what the customer is looking for. If the mandrel is too small for the ID of the tube, you're going to have deformation in the bends then at that point, because now you're no longer taking up that gap on the ID of the tube. You've created more of a gap because that wall thickness is thinner, causing more deformation. Now you can also get it on the high side where the material thickness is thicker, and now the mandrel won't fit. So a lot of times with your aluminums, like your 6061s, you most likely are going to have a couple mandrels on hand to be able to account for those different wall thicknesses. Another challenge is inspection. Inspecting, for example, sheet metal, at 90 degree, just brought it up, you can get your heights easily. Same with tubing, but being that it's round and cross-sectional, it can be a little bit more difficult to inspect, especially as you add bends and rotations. Next thing you know, you have a 45-degree rotation, a 60-degree bend, and another 35-degree rotation, a 90-degree bend, and a 90-degree bend. To lay all that out and get those proper orientations inspected to be able to do an FAI, a PPAP, or whatever it may be for your customer, that can be very difficult to do with rudimentary measuring equipment. So a lot of manufacturers now employ roamer arms with a scanning device, so they can actually scan the bent tube to get the dimensions off of it, and then make the offsets at the bender to bring the tube into spec. Or they also have what they call it's a big machine with a bunch of cameras, and it takes a live picture of the bent tube and instantly will give you all the coordinates and lengths and measurements of that tube to create an offset at the machine. With all that equipment, it makes it very difficult to measure, to inspect tubing. And again, those two pieces of equipment, the roamer arm scanning and then the large scanning machine with the cameras, is really great for prototype runs where the customer doesn't want to invest in check fixturing. Check fixturing is usually used in a larger production runs. That comes in handy for your prototyping and then getting your parts approved for production. And then obviously with production, then you would look at investing in a check fixture. And then that allows the operator to inspect right at the machine, and then you don't have to take time to inspect your quality. With that, we have some videos and questions. Does anyone have any questions currently? Yes?
You talked a little bit about Weld seam.
Yep.
How that affects your bend, elongation, or can you elaborate a little bit?
So weld seam location is crucial on where you place it for bending. So a lot of times, if a customer has holes in a weld seam, you're going to have to orientate that at the laser to make sure that the hole orientation and the weld seam end up in the right spot on the tube bender. Because if the orientation of the weld seam changes between bends, so say you bend one tube and the weld seam ended up on the inside of the bend, then you bend another one and the weld seam ended up on the neutral axis of the bend, and then the next time you bend another one and the weld seam ended up on the outside of the bend, all three of those parts are going to be different in spec. Most likely, two of those three parts are going to be out of tolerance due to the weld seam location. And there's three ways to always look at placing the weld seam. Weld seam on the neutral axis is your first option. That is the best option to take if you can place your weld seam on the neutral axis, meaning that if you're bending to the right, to your left, the neutral axis would be in that bend plane. So the weld seam would be located on the top of the tube. Inside would be crushing the weld seam, outside would be stretching the weld seam. So in regards to that, you want to pick neutral axis for weld seam, compression of weld seam, and then last but not least, your last resort would be stretching that weld seam. Does that help?
Yeah.
Okay. Any other questions?
In your experience, have you found any kind of hard and fast rules with spring back angles as far as progression with bend angle? Like as far as like, the 90 or 3 degrees spring back, does that necessarily mean at 45 you're getting 1.5?
It really depends on the material and how much that material is going to spring back. I mean, sometimes you'll get a 6061 T6 that'll spring 8 degrees, and you have to offset that 8 degrees. The next batch you get in, the elongation might be a little higher, doesn't have as much memory and want to spring back. It'll only spring out 5 degrees. Steels don't spring as much. You're talking maybe 2 to 3 degrees depending on the materials. Aluminums like to spring a lot as well as stainlesses. There really is no hard, fast rule. It really depends. I mean, there is ways around to figure that out. You could run some calculations with the mechanical properties, elongation, tensile, and yield would help you be able to figure some of that out. Does that help?
Yep.
Okay. Any other questions? All right, I'm going to play some videos. Just so everyone can have a clear idea of what all these bending techniques are. So what we're going to play first here is rotary draw bending. As you can see, the clamp die came in, and it squeezed the tube between the clamp die and the bend die insert. It's transitioning, it's straight between the bends. And again, there's slower and faster tube benders. This is a larger tube bender. I believe this is a 5-inch tube bender, so it's going to run a little bit slower. As you get down on your diameters, the machine can actually bend. The machine becomes much faster in its rapid movements. So that is rotary draw. The next is freeform. This is that ceramic die I was talking about. It's on a multi-axis plane. It can rotate, bend on bends. It can also look straight between bends if needed. Again, though, this type of machine, you can get a lot of neat geometry out of this, but you need a higher tolerance. Your rotary draw bends can hold, upwards of or I should say on the lower end, about 30 thousandths over bends. This, you're looking at about 1/8 to 1/4 inch, depending on the material you're forming. It's more for architectural, artistic design, so lawn furniture, things of that nature. In regards to chassis, highly engineered structural tubing, not so much. So this is freeforming. Here's roll forming. So this video is a horizontal roll former. The other benders that we were seeing were CNC rotary draw benders, the first one. You can also roll on CNC rotary draw benders. This is just considered a horizontal roll former. So you can do large sweeping radiuses with this. But on those other benders, you can actually put this same concept tooling on rotary draw and roll tubing out, utilizing a CNC controlled machine. This is all manual roll labor. Very time intensive. The operator needs to be really highly skilled to be able to execute a part of this nature, especially manual roll forming. And then last but not least, this is compression bending. Empty bending, you can never use a mandrel to keep your bends from crushing. Again, as you can see, the bends are actually pretty nice on this one, so wall factor must be low and the degree of bend must be high to allow for not as much collapse on these bends. Those bends are pretty smooth for being empty bend. But as you can see, instead of one bend at a time, it can do multiple bends, hence increasing your throughput. So for higher EAU jobs, these compression bending machines are what the customer is going to want pay in regards to price point. It's used on generator frames. For example, it just folded that hole. Where a lot of times the rotary draw bender, you have to actually do that two separate pieces, swedge an end and then slip fit them together. So that was the videos. Does anyone else have any questions? Yes.
Who are some of the manufacturers of the freeform machines?
What are some of the manufacturers?
I've only found two. I'm just curious. If
There's not a lot around. It's very specialized. Yeah. For example, I think we're one of the only ones in like the Midwest area that actually have a freeform bender. They're very hard to find too. The one that we specifically have, we've had for quite a long time, and I believe it's a Korean machine. But I don't know for sure. I'd have to check that. But yes, you can find rotary draw benders, manufacturers all over. The freeform, that's a little harder to find. Yep.
There's a company called Game Alliance that I've seen, and they have, it's very similar to that freeform bending.
Okay.
Rather than it being a pushing hand.
Mm-hmm.
It's actually just like it's just like a lever kind of, it's just like an arm that comes and pushes it around.
Okay.
And moves it. Would that still be considered freeform? And it actually also extrudes it like diagonally straight up.
That would be. What size diameter were they forming on that type of machine?
It was for like solid material that went up to like I think maybe like half an inch or something.
Okay, so that would be more of a wire form machine that's capable of doing the same things.
Exactly. Yeah, that's what I figured.
Yep.
You were talking about compression bending.
Yep.
Well, originally, when you said compression bending, I thought you were talking about like the old school muffler bender where it pushes it right in the middle of the tube and
Yep.
collapses everything. That there I feel is more like a traditional 2-die, large centerline radius bend.
Mhm.
What's your obviously that gives you a thicker wall.
Yep.
Are there any kind of rules as far as that goes of like ratio of wall thickness to centerline radius? What's the best you can do with something like that? What's the finished wall possible?
That's tough on the ratio because it depends on your material type and everything else. Really, what it comes down to is what are the cosmetic requirements? I mean, you can really some of these really tough bends with a higher wall factor, lower degree of bend, you can bend them out. But they're gonna kink, or they're gonna collapse, they're gonna flatten on the outside radius. So really, at the end of the day, you can bend out a lot of these things, bent if they don't crack. It really comes down to what is acceptable in that bend region.
Right. Yeah, that didn't obviously it's hard to tell.
Yep.
Up close, but that really didn't look that bad.
Yeah, no, not at all.
But it had a larger radius.
Yep, exactly. And if you start to shrink that radius, you'd start to see more of a terminal hump. After where the bend die actually stops bending on it, you'll actually have more of a terminal hump, and then you'd have more flattening on the outside of the radius as well. Does that help?
Yep.
Okay. Any other questions?
Military contractor for do a lot of work with the pool Hueys, so we have to do a lot of rotary bend and tolerance cooling is from Vietnam.
It's from, excuse me?
Vietnam. So looking for okay, guys, is there anything that you would suggest we do with rotary to compression? Or
Excuse me, could you repeat?
Sorry.
What kind of tooling would you suggest?
For
rotary bending, it's got small production run, 6061 T6.
what's the diameter?
It's anywhere from 1/8 of an inch to an inch.
I would go, if you're looking to be able to form that without having any cracking issues,
Yeah.
you'd want to first look at the elongation and make sure it's over at least 20% on that material, and then also just make sure that you're creating your bend die to be at least 3D the OD of the tube. So if it's say it's an inch, you'd want a 3-inch bend die.
Because I have a couple 2D bends that we had to do running into problems.
You'd have to either work with whoever you're getting the material to increase that elongation percentage, or anneal the material prior to bending it. Yes.
If you wanted to apply any wiper dyes or mandrels to your process that you have now, but it's not on the current machine, are there companies out there that are universal wiper dyes, universal mandrels to put on?
Yes.
And
There's
so what would you recommend?
there's quite a few out there, but the ones that I specifically work with are BTI. They're out of Michigan, and then there's OmniX, and they're out of Colorado. They also have a place in the Czech Republic, I believe. But they will make dyes, bend dyes, wiper dyes, mandrels for any machine out there. If they don't have, and what they do is they have specs for all these machines. If they don't have that spec of your machine that you're specifically looking for, they will ask for mounting diagrams, a schematic to be able to look at where all the bolts are mounting, and they'll actually be able to then machine you guys bend dies.
Okay.
Yep. And again, that's OmniX and BTI are two of the main
BTI
ones.
or BY?
BTI. Yep. Yep. Anyone else?